All right, folks, welcome to our next and last video lesson on waves. This is going to kind of put everything together about waves within a medium, waves interacting with a boundary, wave interference, and we're going to look at the phenomenon called standing waves. Now, this is one of actually my favorite things to teach because it actually is very interesting. It gets into the applications of waves in real life, and it's also very applicable to music in how sound and how our ears kind of perceive things. Those of you that play a musical instrument, whether it might be the drums, whether it's the tuba, whether it's guitar, whatever it might be, that standing waves is actually how you produce music. Those of you that might go into music theory, the stuff that we'll talk about today is kind of like the foundations of how music is created. So a standing wave is a phenomenon based on interference. Okay, so interference is what we talked about in our last lesson, is what happens when two waves interact within the same medium. So again, interference is when we have, let's say, a wave that is traveling to the right within a medium that's going to interfere with a second wave that's traveling to the left. So they're going to meet each other within the same medium. And interference is going to describe what happens to those two waves. So remember that when two waves meet in a medium, they can interfere constructively or destructively depending on their phase. And all that happens is their amplitudes follow that superposition principle where they simply add together. So the concept of standing waves, which we're going to talk about today, is an application of interference. The only difference about what we're going to talk about today and what we did last time is that we're not going to look at the interference of like two single pulses. All right, so pulse 1 and pulse 2 that are interfering with each other. We're still going to look at the cases of interference, but this is going to be caused by a continuous disturbance. So imagine I were to hold on to a rope. Instead of just shaking it once and creating a single pulse, I'm going to move my hand up and down and create a continuous pulse. So those of you that might have ever used like an exercise rope or a battle rope, you might have experienced this when you move your hands up and down and it creates like that snake-like pattern within the medium. Well, that snake-like pattern, that is a standing wave. So it's what happens when two traveling waves are going to interfere with each other, but things are perfectly timed up. So to kind of give you guys a visual, here's just a quick little video that's going to show you guys how this works, okay? So you'll see the blue wave and the green wave in there. Those are our two waves that are interfering. You'll see the blue wave is going to the right, the green wave is going to the left, and then you'll see the black wave that shows up. That's the resultant wave of those two interfering. And what you'll see is that that black wave does not appear to be moving at all, but what you see is it crest and trough, crest and trough. It's kind of flipping between those two things. And that's exactly what a standing wave is. Okay, so now to give you kind of a sense of what's going on, this is the simulation you've been using, the wave on the string simulation. So waves, again, are created by a disturbance. So if I create a single pulse, that pulse is going to move within this medium. And again, it's moving back and forth between those two fixed ends. You'll see the wave is inverting. It's flipping from crest to trough and trough to crest every time it hits a fixed end. Again, that's how waves and boundaries interact. So standing waves, again, is a phenomenon that goes along with interference. So what I'm going to do is I'm going to create for interference, I'm going to create a second wave pulse. So let's say I create a second wave pulse right here. So notice that we have now two waves moving through within this medium. It gets a little confusing, but the two waves are just moving back and forth. Now I created it in such a way that obviously they're going to meet in the middle, such that a crest is always going to meet a trough. And you'll see again that if I were to pause this perfectly, you get that destructive interference where they somewhat cancel each other out. So that's interference. Now, standing waves occur when we have a continuous pulse. So I'm going to click on oscillate. I'm going to leave my damping and tension on high, but I'm going to take this frequency and just so we can see it a little bit better, I'm going to decrease it all the way down to 40. And what I'm going to do, and this is set to oscillate. And oscillate is a fancy word for continuous motion. Okay, that's where, like I said, if you ever shake in a rope and create that snake pattern, you're going to move your arm continuously up and down to create those crests and troughs. So I'm going to play here, and you'll see that it's going to create a crest and a trough. That oscillation is moving up and down. Now, what ends up happening here is that I time it up perfectly. Let me just restart this. So what I'm going to do is I'm going to time it up such that every time my crest meets the fixed end on the right, I'm going to create a second pulse that's going to interfere with that. Okay, so it's well timed. And you'll notice that every time it moves up and down, it's doing so at a time when the other wave meets the other end. And notice what happens here. It doesn't appear as if I have a wave moving left and right, but it appears as if all I have is a wave that's stationary in the medium and just moving up and down. So this is an occurrence called standing waves. You'll notice the amplitude. Okay, that amplitude, all that energy is being trapped within that medium. It's all fixed inside there, and you'll see that it's going from large crest to large trough. So I'm going to restart this. This occurs at specific frequencies. So I'm going to change 40. I'm going to move it all the way up to about 80 hertz. Okay, what that hertz again is going to talk about is how quickly that thing is moving up and down. So I want you to notice here that all of a sudden if I increase the hertz, the frequency, the number of waves I'm creating within that medium is going to increase. But I want you to notice here, again, a standing wave occurs when that interference appears to make the wave stand still and just flip between crest and trough. Okay? And I'm going to just move this up one last time to our next frequency. I'm choosing these on purpose, but 1.20 hertz. And again, if I were to press play, you're going to see that those waves interfere. And eventually what you see is this standing wave pattern occur where the wave does not appear to move left or right, but instead appears to just move up and down between phases. So again, this is what's called a standing wave. So standing waves occur when the reflected wave and the incident wave continuously interfere with each other. This is created based on a continuous disturbance of up and down. And it's got to be well timed. When I say well timed, and we'll talk about that in a second, well timed means it only occurs at specific frequencies, doesn't occur every single time. When a standing wave is created, you get these positions where the wave appears to flip between crest and trough. Those positions are what are called antinodes. So you got an antinode here, 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 and here. And then you get those positions where the wave appears to be stationary and doesn't move. Those are the places where destructive interference occurs, called nodes. So you'll see the point here, a node, the point between a node, the point between here, a node. Notice when I put my arrow on it, that wave never moves away from it, and same thing there and there. So you get these places called nodes and antinodes, and that is the location where constructive and destructive interference occur. The node are where the crests and the troughs meet, and these are where the crest and the crest, or the trough and the trough would meet within the medium. So you get constructive and destructive interference occurring at the same time, and again, it's well timed up that my incident and reflected waves are always interfering with each other at that perfectly timed rate. So when I showed you guys that simulation, notice that I chose specific frequencies. I started off with a frequency of 0.40 hertz. And then I went up to a frequency of 0.80 hertz. And then I went up to 1.20 hertz. And I could have kept going, but I stopped. But notice that it only occurred when I chose specific frequencies. So standing waves don't occur at any frequency. They only occur at specific ones. And it's specific to the medium that it's traveling through. So in that simulation, if I were to change the tension or anything like that, then the standing waves are going to be at different frequencies. But nevertheless, the frequencies at which you can create a standing wave, if you were to grab any sort of string, maybe it's a rope, maybe it's a hose, maybe it's a rubber band or something like that, and you were to shake it, you can create standing waves, but it's only going to occur at specific frequencies based on that medium. Those specific frequencies are what are called harmonics, okay? Harmonics, this is where you get into kind of the music side of things. All right, those of you that might know of harmonics or octaves or overtones, things like that. Again, those are what we are using to produce good sounds. So harmonics, again, are the frequencies at which standing waves occur. So the very first harmonic for any sort of string or medium is going to look like this. It's going to be a simple one where you have two nodes at either end of the string. Now these nodes are at either end because, again, my waves were occurring between two fixed ends. And you get one antinode in the middle. This is the very first harmonic or very first standing wave that you can have. Moving on from there, the second harmonic would look something like this, where it now flips in between crest and trough, but notice how I've added an additional phase within there. So by doing so, I now have my two endpoints, which are always going to be nodes, and I've created an additional node in the middle, which added an additional antinode. This would be considered what's called the second standing wave or the second harmonic. So first harmonic, second harmonic, and then lastly I can create the third harmonic, which you're going to see all I'm doing is adding in additional nodes. So I now have 4 nodes, my 2 endpoints, and now I have 2 in the middle, and I add in an additional antinode. So again, what happens here is think of this first one would be my frequency of 0.40 hertz. This middle one would be my frequency of 0.80 hertz. And lastly, this would be my frequency of 1.20 hertz. And again, that was just using the simulation I have. So the idea, hopefully you may have seen, is that there's a pattern between the standing wave or the harmonic that I'm at and the number of nodes and antinodes. So the very first standing wave that I depicted before had 2 nodes, which were my endpoints, and 1 antinode in the middle. And that was the flipping between crest and trough. So it looks like this. The second harmonic, which is my second standing wave, I added in an additional node in there, again, my 2 endpoints and then 1 in the middle. And that also increased the number of antinodes. Key thing here is that between, say I have, 3 nodes, call these nodes, between every node, there needs to be an antinode, okay? So that is one thing that has to be true. So if I add in a node, I have to add in an antinode, okay? But you'll notice the pattern that as I go to these different harmonics, as I go to the different standing waves, the number of nodes is going to increase by 1. The number of antinodes is also going to increase by 1. You'll notice that the number of antinodes, n, is always going to equal the standing wave pattern or the harmonic that I'm at. So if I'm on the 6th harmonic, that means I need 6 antinodes. Count here, 1, 2, 3, 4, 5, 6. But the number of nodes is always going to be 1 greater because I have my 2 endpoints. I would have 1, 2, 3, 4, 5, 6, and 7. And that's going to account for any standing wave or harmonic that we're looking for. Okay, so our first example is going to be just practicing this. Now, I know I gave you guys the chart before, but let's say I want you to recognize the standing wave patterns based on the harmonic. So here, if I'm asking for the third harmonic, the third harmonic, in order to draw this, is all about the number of nodes and antinodes. So based on that previous chart, what we should know is that the number of antinodes is going to be 1 more than the harmonic we're on. So if we're on the third harmonic, that means we're going to have 4 nodes. Now the nodes are going to be my places of node displacement, which means they're going to fall on the string. Now know that based on what we did, the 2 fixed ends, the fixed ends are always going to be nodes. So what that means is I have to squeeze 2 more in here, and I want to make sure they're split evenly. Now to do this, what ends up happening is that in order to add 2 more here, what I'm going to do is I'm cutting this string technically into 1, 2, 3 parts. So just a little side note here, notice that I'm cutting the string into thirds. Third harmonic, cutting the string into thirds, get out of town. All right, next I want to draw the antinodes. So know that between every node, there's an antinode. So if there's 4 nodes, that means there's going to be 3 antinodes, and that's always going to equal the harmonic we're at. So the antinodes would be those places of maximum amplitude or maximum displacement, and depends on, I can start with a crest or a trough, it doesn't really matter, but between every crest, there has to be a trough. It's got to fluctuate in between. But once I draw those antinodes, now I can sketch my wave. It's going to go up and down through the nodes, through the antinodes, and like that. So notice my third harmonic, we're going to have 3 chunks in here. So I split it into thirds, but that's what it would look like. And it's going to fluctuate between crest and trough. So I might also draw these loops going down and up and down. It's going to fluctuate in between those. Okay? Now, next one says draw the 6th harmonic. So the 6th harmonic, again, it's all about the number of nodes and antinodes. Give myself a little more real estate here. So know that we're going to have 2 nodes at either end. And again, if it's the 6th harmonic, that means we're going to have 7 nodes and 6 antinodes. This one's going to be a little bit more difficult to draw, but we're going to take this length of string and split it into 6 equal parts. So again, I'm going to have my 7 nodes, which are shown there, and I have 6 equal parts, 1, 2, 3, 4, 5, 6, which is why we have the 6th harmonic. We have 7 nodes, but 6 chunks of that string. And again, lastly, between every node, we're going to have an antinode that's going to alternate between crest and trough. So if I were to sketch this way, it would go up and down. And notice here as I'm drawing this, okay, you can just see that the 6th harmonic, based on the number of nodes and antinodes, that the frequency got bigger, right? Larger number of crests and troughs means it was more frequent that I had to go up and down between them. Okay? Don't worry about the amplitudes that I draw. I don't have any information about the amplitude, so I'm just sketching those crests and troughs. But again, standing waves, it's all about the number of nodes and antinodes to get those different harmonics. Now to connect standing waves to frequency, again, those harmonics are all about the frequency at which those standing waves are going on. So now we're going to just do the same sort of things. We're not necessarily going to think right away about nodes and antinodes, but we're going to look at the frequency and see if we can figure out the harmonic we're at, and we'll draw those nodes and antinodes at the end. So here it says I have a fundamental frequency. Okay, fundamental frequency is a fancy schmancy way of saying the very first harmonic. Okay, so anytime you might see that, that is the very first harmonic. And I guess it's worth noting that every sort of medium is going to have that fundamental frequency. And if you go back to like a guitar string, depending on the string that you strum, if you will, it's going to vibrate at its very fundamental frequency, that very first standing wave or first harmonic. Okay? And then different frequencies beyond that are all going to be based upon that fundamental. So here it says the fundamental frequency is 80 hertz. If I were to kind of sketch that, that first harmonic again would look something like this. So I want to know, what would the harmonic look like if I were to have a frequency of 240 hertz? Oopsie daisies. So 240 hertz, what I want to do is I'm going to relate that to the fundamental frequency of the first harmonic. I know that 240 hertz, when I compare that to 80, let's say I just take and divide those two numbers out, I'm going to get 3. I know that 240 is 3 times bigger than 80. That means that we're going to technically be on the 3rd harmonic. Okay, now what does that mean in terms of the wave pattern? Well, the 3rd harmonic, remember, is going to have 2 nodes at the endpoints, no matter what, in terms of this string. But we're going to have then 2 nodes in the middle. So remember that in terms of nodes, we're going to have 4 nodes, and we'll have an equal number of antinodes. So the 3rd harmonic, again, is going to break this string into 3 chunks. 1, 2, and 3. Then between every node, again, there's always going to be antinodes. So to draw my wave pattern would go up and then down, crest and trough, until we reach the end. Okay? So again, looking at the nodes and the antinodes, all I'm doing is comparing the frequency. The neat thing is that any harmonic is always going to be a multiple of the fundamental frequency. Okay, and the number harmonic we're on is going to be that number multiple of that fundamental frequency. A way to kind of think about it is this. Think of whatever harmonic we're on, whatever frequency is going to be that harmonic times the very first frequency, the very fundamental frequency. So I can get a little bit mathy with that. All right, next one. We have here the fundamental frequency is now 120 hertz. So different string is going to vibrate at a different frequency. All right, and then we want to find what does the pattern look like at 840 hertz. So just like the last one, I'm going to take 840 hertz, and I'm going to compare that to 120 hertz. I want to figure out how many times bigger is 840 compared to 120. By just simply dividing those two numbers out, you're going to get the number 7. Whoa! Now this one's going to be a little bit tough. That means we're on the 7th harmonic. 7th harmonic means we're going to have 8 nodes, and we're going to have an equal number of antinodes. So drawing this is going to be a little bit tough. So here would be what the nodes look like. So notice I have my 2 nodes at either end. Then I had to fit in here a couple more to just make 1, 2, 3, 4, 5, 6, 7. So I had to break that into 7 chunks. Obviously, by giving that length of string to you, it's a little bit more difficult to draw, but nevertheless, the idea is counting the number of nodes and antinodes is where it's at. That we're always going to have one more node and an equal number of antinodes. So now when I fill in my antinodes in between, I'm going to have 2, 3, 4, 5, 6, and 7. So now to draw my wave is between every 2 nodes is an antinode. And notice how, in terms of the frequency, that when I start to add in more nodes, I had to draw a wave more frequency. So drawing it's helpful because then you get that relationship between the standing wave or harmonic we're at and the frequency. All right, as I mentioned before, this idea of standing waves and harmonics is something that is very relatable to music. So I have here a little video that's going to show the harmonic series played on a C string of a cello. Okay, so you're going to see a gentleman that's going to be playing a single string. He's going to be playing different notes on it. Okay, and you're going to hear a different sound every time. What I want you to do is I want you to look at his hand placement and think about what we just went through in that last example. So here we go. Enjoy. We're going to watch it once, and then I'm going to talk through it a second time. Okay, so now watch the hand placement. I'll talk through this. We have 2 notes. Cut it in half, the second harmonic. Cut it in third, the third harmonic. Fourth harmonic. Fifth harmonic. And sixth harmonic. Oh, and 7th harmonic. Oh, and 8th harmonic. Oh, isn't it beautiful? Isn't it beautiful how all this stuff can be related back to real life? Those of you that are in music, hey, how about that, huh? All right, now this is the last piece of the puzzle. So again, I talked about standing waves, the different nodes and antinodes. We looked at the frequency. But we do hopefully remember that there is that relationship between frequency and wavelength. So now we're going to get in kind of the mathematical side of things. It's nothing that's crazy too difficult. Okay, but each of these standing waves are going to occur at different frequencies. And that as we get to higher standing waves, the frequency is going to increase. So we're going to see an increase in the frequency, but there is a relationship between frequency and the wavelength. And remember that they are, as long as they're in the same medium, there's an inverse relationship between them. That an increase in frequency will cause a decrease in the wavelength. So think of this first as our length of string. I want you to notice that this is the first harmonic. And the first harmonic, what we have is a single crest or a single trough. So in terms of wavelength, this is technically a half of a wave. Okay? For the second standing wave, we have now added in an additional node. We now have a crest and a trough. So notice here that I have 1 complete wavelength. And then lastly here for the third harmonic, if I were to continue, I add an additional node, but now I have 1.5 waves. So I'm going to say here 3/2 wavelength. 3/2 is 1.5. Okay? So there's a relationship between the length of the string we're using and the wavelength. So here the first standing wave is half the wavelength. This is 1 full wavelength, but I'm going to write it as 2/2. And then I have 3/2. So I want you to notice the pattern. The first standing wave, this first harmonic, second standing wave or second harmonic, and the third standing wave or third harmonic. So the number of harmonic we can relate between the length of the string and the wavelength. So this is the kind of the mathematical relationship between these two things. So there's multiple ways we can write this. So this is relating the length to the wavelength, okay? You might also see this equation written in terms of the wavelength, that the wavelength, if I were to just kind of rewrite this, would be 2 over n times the length of the string. What that means is that for example, the first harmonic, my wavelength would be twice the length of the string. And this is something we did early on in this chapter. Here, if this is my standing wave, I have one complete wave, so that means the length is equal to my wavelength. And then lastly, the third harmonic, again, I have a half, a full, and a half, so I have 1 1/2, so that means 2/3, right? 2/3 of this length would be my wavelength. So again, this is another way in which we can look at that same relationship. The thing that's going to be helpful for us is to understand the relationship between the wavelength and what harmonic we have. So for example, if I were to give you information about the wavelength, how do we know what harmonic we're on? So this is actually the way I like to represent this equation, is I'm just going to rework these, these letters again, or this formula, and the number harmonic we're on, call it n, is going to be equal to twice the length divided by the wavelength. And this is the way we're going to actually use this equation. And why it's helpful is this. Let's think back to this very first example. Here I have my length of string, all right? And this length of string represents half the wavelength. So if I take one of those lengths and I double it, I'm going to get the wavelength. So my first harmonic would be twice the length divided by that wavelength. Well, those two things would cancel out and give me 1. I know I don't have numbers there, but that's the idea. It will tell me what harmonic we're on. So to kind of relate this to our last example here, is let's say I give you the length of the string and the wavelength of the harmonic we're at. Can we draw this pattern? So here you are told that the wave or the string has a length of 48 centimeters. So think of that as L. And then we have a wavelength of 32 centimeters. Think again of that as lambda. So if I want to find the harmonic that we're on, we can use this simple relationship, 2L over lambda, 2 times the length over the wavelength. So I would do 2 times 48 and divide that by 32. So that would give me 2 times 48 is 96, divided by 32 is going to give me 3. So that means this is going to be the third harmonic. Now, third harmonic, if we relate this, okay, third harmonic, again, with my 2 endpoints, is going to have 4 nodes. So I'm going to add in here, boop, boop, those 2 extra ones. So again, it's going to split this string length into 3 chunks, and then again, between every node, there's going to be an antinode. So then I can draw my wave pattern to look like that. Again, not the prettiest, but that's the idea. So based on the length and the wavelength, we can figure out what harmonic we're on. Next example, if I have a string length of 64 centimeters, I'm going to draw the wave pattern for the wavelength of 128. So again, think of this as my length, and 128, that is the wavelength of whatever harmonic we're on. So using the formula, n equals 2 times the length, so 2 times 64, divided by 128. So if I do that, 2 times 64 is going to give me 128. Divided by 128 should give me 1. So that means that I'm on the first harmonic, the first standing wave. The first standing wave will have 2 nodes and will have 1 antinode. So this would be half the wavelength. Okay? So again, this is relating wavelength to that idea of the harmonics. All right, folks, I tell you, that was so much freaking fun talking about standing waves. I enjoyed it. I hope you did too. I know you did. I know right now you're so excited. But again, this is where it kind of gets fun when we start talking about waves, because now we're going to get into things like related to music and all that. It's kind of some cool stuff. So, guys, got any questions, like always, jot those things down. If you need to go rewatch some things, go ahead and do it. Otherwise, good luck on those concept builders, and we'll see you guys next time. Peace out.